Hey everyone, me again, Mrs. Hanson, with some wrap-up information, some last topics in Chapter 4. Some of these words we've already been alluding to earlier when we were drawing Lewis dot structures. I was talking about picking the least electronegative element to place in the center of your Lewis dot structure and attach back all of the other atoms to it. And finally, I'm going to define the term electronegativity. The electronegativity of an element simply tells me about the atom's ability to attract electrons towards itself in a shared pair of electrons in a covalent bond. It tells us, in other words, how much a particular atom wants the electron, right? So how attractive are you in gaining electrons towards yourself? So think about increasing electronegativity, and we have the strongest of strong nonmetal over here, fluorine. Fluorine is the most attractive element to electrons. It's the strongest of strong, the most attractive nonmetal, gaining electrons, pulling electrons towards itself. So the closer you are to fluorine, the more you have an ability to draw electrons towards yourself. Let's explain why. Remember the atom of fluorine with its atomic number 19 is its mass number, just to try to think about what it's got. It's got 9 positive protons. It's got 10 neutral neutrons. And if you just think about the arrangement of electrons, they're giving an outer arrangement of 2, then 7. We have 2 valence, 2 shells, if you will. 2 energy levels, would that be a better word that we're used to hearing? 2 energy levels, period 1, period 2. Now with 9 positive protons in only 2 shells kind of protecting those protons, these protons are the most exposed, and that's what's going to draw electrons towards itself, right? Exposed protons draws electrons. Now think about what I'm saying. If we have fluorine with 2 valence shells around its, period 2, then if we go down a period, we've got chlorine and it's got 3 valence shells. That's why it's getting bigger. Bromine has 4 valence shells. That's why it's getting bigger. Iodine has 5 valence electron shells. That's why it's getting bigger. That those protons become more and more shielded and less likely to be able to attract someone else's electron towards itself. So these protons are least shielded by the electron shells covering it. Fluorine with its 9 protons. Of course, oxygen is small, but it only has 8 protons. Nitrogen is small, but only has 7 protons. More protons, the more ability it has to draw electrons towards itself. So fluorine is the strongest of strong nonmetal. Notice the trend. Electronegativity increases as you go up and increases as you go across. Fluorine, the strongest of strong. You can also just draw an arrow like this. That's the trend. The closer you are to fluorine, the more electronegative you are. And I placed one of these in here for you in your notepad. And I don't really think you rely on the numbers so much as you rely on a trend. The closer you are to fluorine, the more electronegative you are. If you rely on the trend, you'll be able to predict the answers without having to know these specific numbers. If we look at electronegativity as it increases across a row and it increases going up a column as atoms get smaller, with fluorine being the most electronegative element. Just use those trends, really without even understanding the numbers. You don't have to memorize those, but just use the trends. Rank the following atoms in order of increasing electronegativity. So increasing means lowest to highest. And of course, highest would be who's closest to fluorine and who's the furthest away. So let's look at number 1. We have lithium, we have sodium, we have hydrogen. We know that electronegativity increases as you go up a column. That's our trend that we just wrote in our notes. Increases as you go up. So the lowest would be sodium. It's the largest atom. Its protons are shielded. Then lithium, then hydrogen. And you can verify that with your electronegativity numbers. But without the chart, that's what you're looking for. Don't rely on the chart. Understand the trend. It increases going up a column. Let's compare an oxygen, a carbon, and a beryllium. So now all of a sudden we're looking at the same row, and this is the trend. We have to work to remember that electronegativity increases towards fluorine. Furthest away, then carbon, then the closest, oxygen. Find the periodic trends. Next one we're examining, we're given chlorine, we're given iodine, and we're given fluorine. The trend, electronegativity increases going up a column. The least electronegative, chlorine in the middle, and then the most electronegative being fluorine. And one more trend, we have a boron being compared to an oxygen, being compared to a nitrogen. Left to right, boron, then nitrogen, then oxygen, increasing electronegativity as we read left to right on the chart. Well, these electronegativity values are used to determine the distribution of electrons in a shared pair called a covalent bond. So if the electronegativities of two bonded atoms are equal or they're similar, the bond is said to be nonpolar. And I'm going to just define that as saying it's an equal distribution of electron charge in both directions. And that's really what our definition of a covalent bond is. So here we're writing down, good set of notes here. It says nonpolar. A nonpolar bond. A nonpolar bond means we have an equal distribution of electron charge. The electron clouds are evenly distributed to both atoms in the shared pair of electrons known as a covalent bond. Now, of course, if you have a like atom bonded to itself, the electronegativity difference is going to be 0. Electronegativity, En. The En difference of 0 means it's nonpolar. The other very common nonpolar bond that you should just remember is a carbon to hydrogen. The electronegativity difference is only 0.4 between a carbon to hydrogen. That's a very insignificant value for electronegativity differences, so that is also considered a nonpolar bond, a very small difference between C and H. That means that the bond has an equal distribution of electrons between the two atoms that are sharing the pair. So nonpolar bonds, an equal sharing of electrons, equally shared between two atoms. You need to remember any atom bonded to itself would have a 0 difference, and carbon to hydrogen is also a very common example of a nonpolar bond. If bonding between two atoms of very different electronegativity values occurs, we end up with what's called a polar covalent bond, or called a dipole. This is an unequal distribution of electron density. In the covalent bond, the more electronegative element is going to be able to pull the electron density towards itself, creating an area that's much more rich in negative charge and an area that is deficient in negative charge. For example, oxygen with its electronegativity value of 3.5, and carbon with its electronegativity value of 2.0. 3.5 minus 2.0 gives me an electronegativity difference of 1.5. The electronegativity difference is 1.5. That to me is a significant enough value to create a polar covalent bond. Covalent means it's still being shared, but not equally. And we start to see this symbol to denote a polar bond. Between the carbon and the oxygen, notice we have a little tail at the end of the arrow that looks like a positive sign. That tells me that the more electronegative element oxygen is very rich in electron density. This is a Greek symbol. It's a lowercase delta, just in case you wanted to know. In the Greek alphabet, in the lowercase Greek alphabet, it's a delta sign. Capital delta, lowercase delta. This means, the little delta sign means partially negative. And over here, this guy is going to be partially positive, just based on the unequal distribution of the electrons between the shared pair. Oxygen is stronger than carbon. It's so strong, it's pulling the electron density towards itself, creating a very rich negative region on the oxygen, and leaving the carbon a little partial, it's a partial positive, my bad. Partially positive because it's lost its electron distribution. So when we have a bond where the pair that's being shared, a shared pair, is unequally distributed between the two atoms, we call it a polar covalent bond. The electrons in the bond are unequally shared. Those electrons are being pulled towards the oxygen, which is far more electronegative, and it gets this little Greek symbol to represent partially negative. And since the electrons are being pulled away from the carbon, the less electronegative element is going to be left with a partial positive sign. So the polar bond gets a symbol, and then the area in the molecule also gets those symbols. And let's put it together in terms of a quantitative value. In the left column, we see an electronegativity difference, which you often see just abbreviated as EN, electronegativity difference. If I subtract two elements that are in a bond together and get less than 0.5 for an electronegativity difference, we're going to call that a nonpolar bond, and that those electrons are being shared equally. A moment ago, I gave an example of a carbon to hydrogen bond. The carbon with its electronegativity value we said was 2.5, and the hydrogen's electronegativity value was 2.1. When we subtracted that, we got 0.4 for the electronegativity difference. Well, certainly that's not a significant value. It's considered to be an equal distribution of charge between the two atoms. It's a nonpolar bond. If we subtract two elements that are bonded together and come up with a value greater than 0.4, so let's say 0.5 to 1.9, just slightly less than 2, these are now called polar covalent bonds. Let's suppose I have a molecule that's, let's do HF. Fluorine with its electronegativity value of 4.0 and hydrogen with an electronegativity value of 2.1. When I subtract those two, that's 1.9. That's our electronegativity difference. And so clearly you see that that is an unequal distribution of charge, and you would represent that as a polar covalent bond, so much so that you'll start to see the electron distribution being pulled towards the fluorine. This is a very rich electron area, leaving the hydrogen as electron deficient and partially charged. So this would be called a dipole. It has a region that's partially positive and partially negative. A polar bond is formed. And then if we have kind of such a large electronegativity difference that the electrons aren't being shared at all, they're being transferred, we call that an ionic bond. So for example, if I were to have a compound built of sodium fluoride, NaF, sodium with its electronegativity value of 0.9 and fluorine with 4.0, when I subtract 4.0 minus 0.9, we get 3.1. Clearly, that's bigger than 2, so this is now an ionic bond. We knew that. It's a metal to a nonmetal, a positive and a negative. So we already suspected it was ionic based on the fact we had a metal with a nonmetal. And again, rely on the trends that we know more so than worrying about memorizing electronegativity values. Using these values, calculate. If you need to, we could just calculate or rely on trends. Are they nonpolar, polar, or ionic? So let's model HF. We said this a moment ago. We calculated hydrogen with its 2.1, fluorine with its 4.0. When I subtract the two, I got 1.9. We called that a polar covalent bond. And I even drew that saying, boy, this is so polar covalent. Hydrogen is left partially positive, and the fluorine is partially negative. But we knew it was covalent because it's two nonmetals. Right? Nonmetal to nonmetal makes a covalent bond. Next one is MgO, magnesium oxide. Magnesium, 1.2. Oxygen, 3.5. .3 is our electronegativity difference. Well, that definitely falls in the ionic bond. But you know that. Rely on your lessons so far. A metal to a nonmetal is an ionic bond. Magnesium doesn't share its electrons. It wants to just give them away, and oxygen will take them in. Letter C, we have a fluorine bonded to itself. Clearly, electronegativity difference is going to be 0 when I subtract an element from itself. So this is a nonpolar covalent bond. ClF. When I'm bonding fluorine and chlorine, the electronegativity difference is 1. So this is also a polar covalent bond. Two nonmetals, polar covalent. Water is attached as HOH. So the bond there is a hydrogen to an oxygen. Oxygen with its value of 3.5, hydrogen with its value of 2.1, we get 1.4. That is a polar covalent bond. Two nonmetals, we knew it would be covalent. And here's ammonia, we've drawn several times. So it's an NH bond. Nitrogen to hydrogen, 3.0 minus 2.1. This comes out to be polar covalent. Relying on the trends and making sure that you see metal to nonmetal, ionic. Nonmetal to nonmetal will be covalent. And if it's a difference in polarity, it's polar covalent. And two elements that are similar, such as a fluorine to fluorine, or even a carbon to hydrogen, you can count that as nonpolar. Try these on your own. Will they be a pair of elements as polar covalent or ionic? Now I know it says using electronegativity values, but you can just rely on the chart and what we know, metal to nonmetal, ionic. Nonmetal to nonmetal, covalent. Let's see if that falls. Let me finish writing that. Let's see if it falls true. So hydrogen, 2.1. Bromine, 2.8. That's an electronegativity difference of 0.7. That's polar covalent. We knew that. Nonmetal to nonmetal. Nitrogen, 3.0. Carbon, 2.5. Electronegativity difference of 0.5. That falls as polar covalent. So we knew that. Nonmetal to nonmetal. Let's see, how about sodium and sulfur? 2.5 for the sulfur, 0.9, 6, 1. That's a little tricky there. I would definitely say that falls in the polar covalent realm because it's not bigger than 2. And then lithium and oxygen. Let's see, oxygen 3.5, lithium, oh yeah, here we got one there. This is ionic because it's bigger than 2. Alrighty, so we had one tricky one there. We had to rely on the electronegativity values. So perfect work there. We're getting the hang of this. And so as we kind of focus on identifying bonds as polar or nonpolar, we're going to move that to a larger view of the entire structure. Is the molecule polar or nonpolar? Does the molecule have an equal distribution of electron charge, or do you see a molecule that has more negative in one region, more positive in the other region? So not only can we talk about the polarity of the individual bonds, we can talk about the polarity of the overall shape of the molecule. Polar molecules have an unequal distribution of electron charge through the molecule, regions of electron-rich density and regions of electron-deficient density. Nonpolar molecules have an equal distribution of electron charge. Think symmetry. If I stand in the center and I look out in all directions, are they all the same or are they different? Nonpolar is a completely symmetrical molecule. And if you see anything unsymmetrical, I mean like a little bit something more interesting in one area than something more boring in the other, then you're going to look at some polarity of that molecule. So look at what I'm showing. Here's a central atom, and I look up and I look down, I look left, I look right, and they're all the same. This is a perfectly symmetrical molecule. The carbon has 4 domains. Each of those domains are exactly the same, all leading to hydrogen. This would be a nonpolar molecule. And it is also made of nonpolar bonds. C's and H are nonpolar bonds. The whole molecule itself has an equal distribution of charge, so it's nonpolar. What if now we look at removing one of the hydrogens and replacing it with a chlorine? Do you notice this very rich region of electron density on that chlorine? There is a significant electron distribution toward the chlorine. So this is a polar bond. And this here is a very rich region of electrons. So that's a very negative region, making this region a very positive or electron deficient region. So this is a polar molecule because there is an unequal distribution of electron charge within the entire structure. Polar molecules are not symmetrical. And by that I mean, of the 4 attachments to the carbon, one was different. And as soon as I had something different, something a little more interesting to look at, I now knew that the molecule would be polar. Polar or nonpolar, our question asks us. And the secret lies here in being able to draw these Lewis dot structures. So when I take carbon with its 4 bonds, I can see that it would lead down to hydrogens, getting oxygen, the 2 bonds and 2 sets of dots it requires. We ended up drawing a carbon leading up to an oxygen by double bond and 2 single bonds to hydrogen. Just to review, the Vesper count would be 330. We would call this trigonal planar. Just trying to sprinkle in all of the lessons along the way. Bond angle, 120 degrees. Do you notice that this is a very polar bond with the more electron density oxygen? This is a very rich region of electron distribution, making these hydrogens partially positive, right? The entire electron draw is up towards the very electronegative oxygen. So this indeed is a polar molecule, and it has a polar bond between the carbons and oxygen. This time when I draw boron trifluoride, boron, who lives in group 3A, has 3 valence electrons. Remind yourself why there's only 3 dots there, because boron lives in group 3A, so that means 3 valence electrons. It will be an octet rule breaker. It wants to only have 3 bonds because it has 3 dots to begin with. This on the Vesper count, 330, we call this trigonal planar. Bond angles of 120 degrees. Now here's the trick. Just stand in the center. You have 3 things to look at, right? 3 domains. I look up at a fluorine, I look down at a fluorine, I look down at a fluorine. They are all the same. This is a very symmetrical molecule. Nothing interesting to look at from any other direction. It's all equal distribution. So this is a nonpolar molecule. Now let me emphasize, these are still polar bonds, right? These are still bonds that have an equal distribution, but in all directions. So the boron, even though it's covalently bonded to fluorine, it's being pulled, the electron distribution towards the fluorine, but it's in equal directions. So because the electrons are being drawn equally in all directions, it ends up to be a nonpolar molecule. If you compare that to this guy, here's the ammonia molecule we have drawn numerous times. It has a Vesper count of 431. We called that trigonal pyramidal. So therefore, I do have these very electronegative differences here, that these are polar bonds, and the electron distribution is coming up towards the nitrogen. And do you see this big old lone pair of electrons making this a very rich region? Because there's 4 bonds, four domains, and only 3 lead to atoms, this is not symmetrical. There is something different when I stand and look from the central atom. I stand at nitrogen and I look up, I see lone pairs of electrons. That's different than seeing the hydrogens. This makes this molecule polar. The bonds are polar and the molecule is also polar. And the last one we'll draw, a molecule that is attached to 2 chlorines and attached to 2 hydrogens, CH2Cl2. Now clearly I can see, when I consider the tetrahedral 440 tetrahedral molecular geometry, that I have this region that's very rich in electrons, that the electrons are being pulled away from the carbon towards this chlorine. Electron rich makes this area very negative. And the same story here, this distribution is being pulled towards this very electronegative element chlorine, making this a very partially positive region over here for the hydrogens. This is a polar molecule. I have two polar bonds, and the entire structure is also polar. Polar means an unequal distribution of electron density around the entire structure. We have a very rich region of electron charge on the chlorines and a very deficient electron distribution on those two hydrogens. So we said polar, nonpolar, polar, polar. Same idea. Here notice that we have an example now where we're given 3 atoms in each of these structures, but to determine polarity, look for the geometry. That's my clue here is before you answer, consider the molecular geometry. Oxygen, group 6A, 6 valence electrons. That means that I'm going to have 2 dots, 2 bonds. And we've drawn water enough to know that when I draw it correctly, those 4 valence electrons, or 2 sets of dots, make this molecule bent. That the molecular geometry is 4, 2, 2. Seeing that allows me to predict this is a very rich region of electron density. These bonds are very polar, pulling up towards the oxygen, making these hydrogens electron deficient. Water is all kinds of polar. Carbon dioxide, remember carbon with its 4 bonds. Oxygen requires 2 bonds, 2 sets of dots. Here's our carbon dioxide. 2,2,0 is its molecular geometry, is linear, bond angle of 180 degrees. So this carbon only has 2 domains, not 4, like the oxygen had 4 domains. And this was not symmetrical because it had 2 things that were different than the other 2. 2 lone pairs, 2 atoms, that's not the same. But if I stand here at this carbon, I only have 2 directions to look out. I do have polar bonds. Those bonds are polar. The electron distribution is being pulled away from the carbon towards the oxygen, but it's an equal but opposite, right? Equal but opposite pull. So it's an equal distribution of electron charge. This is a very symmetrical molecule. There we go. So we said polar and nonpolar. And the secret lies on drawing it out. Make sure you draw before you just decide if something's polar or nonpolar. Go ahead and try these last few practices. Come on back to me when you want to check. You have a few more to finish off. You have a little bit of reading on page 14 as well. Pause the video, practice these polarity molecules. Come back when ready to check. Okay, so that means you've drawn them. If you've cheated yourself and not drawn them, shame on you. I'm going to just laugh at that, but please make sure you're practicing drawing and don't just watch me. Chemistry is not a spectator sport. I see that this is indeed a polar bond, so I'm going to just use red. I'll call this a polar bond. That's the designation for the polar bond. The molecule itself is also polar with an unequal distribution of electron charge, very rich electron distribution around the chlorine, a very deficient electron distribution around the hydrogen. C2H6, our molecule looks like this. We'll learn to call that ethane in organic chemistry, a hydrocarbon. This is a non-polar molecule. It is a very symmetrical molecule. All bonds are non-polar. Pretty unexciting molecule. Letter C, I have a carbon leading out to 2 hydrogens, leading out to 2 fluorines. a tetrahedral 440. Tetrahedral. Fluorines are very electron rich, the strongest of strong nonmetals. So the polar bonds between the carbon in each of the fluorine create this very rich region of electron cloud around the fluorine, a very deficient region of electrons around the hydrogen, making this molecule polar. HCN you drew. Carbon with its 4 bond requirement, nitrogen with its 3 bonds and 1 set of dots, you knew to draw a triple bond. Here we have a very polar bond between carbon and nitrogen. You can see that this here creates a very rich region of electron density. The hydrogen, a very electron deficient. This is a polar molecule. And finally, carbon tetrachloride, the central atom carbon, leads to 4 identical chlorines, making this a very boring molecule, a non-polar molecule. Now I'm going to finish these dots and then remind you we were also asked about bond polarity, and each one of these is indeed a polar bond. It's just that all the distribution is going in an equal direction. So because it's a very symmetrical molecule, it ends up to have an equal distribution of electron charge all around the entire structure, making it a non-polar molecule. And the last, you're just looking at determining whether bonds, and well, those are the answers we just drew. The last one, I think we'll just draw it by hand here. Let's see, I have a carbon to carbon, leading chlorine, chlorine. As I look over this, it's very similar to one we drew earlier, letter C up above. So I have polar bonds between the carbon and the chlorine. Trying to get all my dots down, I get distracted there. I can see that I have polar bonds, and those are leading out but equal directions. So the molecule is non-polar, but I do have polar bonds between the carbon and chlorine. The carbon to carbon, of course, is non-polar. Then I see one last structure where hydrogen is attached to 3 H's. It leads to a carbon, double bonded, chlorine. Oh yeah, all kinds of exciting things. All right, so here this needs some dots. This needs some dots. I can clearly see this is a region that's very negative. This is also a region that's very negative. This is a polar bond. This is also a polar bond. And then this is all kinds of boring over here, isn't it? So this is going to be electron deficient, with all the electron being pulled towards the very exciting part of the molecule, the oxygens and chlorines. So this molecule is polar. So the last thing you need to do to finish up your notes, if you have any holes in that notes, if we didn't finish anything together, it's your job to go back and make sure that that's all completed. You have a 4.9 to focus on health and medicine to finish page 14. And when ready, you're going to submit your note pack, and I'll be happy to read it. Okay, keep up the great work, everyone.